My name is Selda Oterkus. Today I will present effect of horizon shape in peridynamics. Before I start my presentation, I would like to acknowledge my co-authors, Mr. Bingquan Wang and Dr. Erkan Oterkus from University of Strathclyde. Before I start, I would like to give you a brief outline of my presentation. First, I'll give you a brief introduction to Peridynamic Theory. Then, I'll present state-based peridynamic formulation. Then, I'll explain our findings about the investigation of effect of horizon shape. Next, I'll finish my presentation with final remarks. So, what is peridynamics? It's a non-local continuum mechanics formulation. In peridynamics, we use integral equations rather than partial differential equations. Therefore, whether we have discontinuity or not, equations apply everywhere. And peridynamics is especially good for predicting failure. And we don't need to use any crack-growth law for failure prediction. With respect to classical approaches, the way we define failure is very simple. A simple failure criteria is sufficient for predicting failure. And therefore it is very suitable for crack initiation and propagations, and also multiple cracks can easily interact with each other. As I said, peridynamics is a non-local continuum formulation, and according to continuum formulation, a body is composed of material points. In peridynamics, a material point not only interacts with material points in its neighborhood, it also interacts with all the material points through peridynamic forces. In classical continuum mechanics, we are trying to solve this first equation in the slide to find deformations, strains, and stresses, and the internal forces are taken into account through traction forces. However, if there is any discontinuity in the structure, like cracks, the derivative in this term is not defined, so we cannot use this equation anymore. In order to overcome this problem, in peridynamics, we replace this problematic term with an integration. Since this is an integral equation, it is always valid even if there is a crack in the structure or not. Here, instead of traction vectors, we have peridynamic forces between material points, as shown in the second equation in the slide. Peridynamic theory is a continuum theory. Therefore, the body is composed of infinitely many material points. In peridynamics, all material points can interact with each other. However, if the distance between two points gets larger, the interaction force gets smaller. And we define a region called horizon, as shown in here with yellow region. Therefore, we can ignore the interactions outside of this region. Depending on the peridynamic forces, we can classify peridynamics. If the peridynamic forces that two material points acting on each other are in different directions, we call this non-ordinary state-based peridynamic theory. If we assume that these peridynamic forces are along the interaction direction, but their magnitudes are different from each other, we call this ordinary state-based peridynamic theory. And if we have further assumption that these forces are equal and opposite to each other, we call this bond-based peridynamics. And bond-based peridynamics is simple, but it has limitations. In bond-based peridynamics, we can express the peridynamic force between material points in terms of peridynamic material constant and stretch. Here, C is the material constant, which is a function of elastic modulus and horizon size, and S is the stretch, which is defined as change in length between two material points divided by the original distance between them. We can assume that peridynamic force is along the direction of peridynamic bond in the deformed configuration. In ordinary state-based peridynamics, we can express the peridynamic force between material points in slightly different form. Here is the equation of motion in ordinary state-based peridynamic form. The first term on the right-hand side is the force that material point x prime is exerting on x. The second term on the right-hand side corresponds to peridynamic force that material point x is exerting on x prime. And here we can express the peridynamic force expression in terms of peridynamic parameters and stretch. Here A, B and D are the peridynamic parameters, delta is the horizon size, S is the stretch term, and theta is the peridynamic dilatation expression, which can be calculated as shown in the slide. For non-ordinary state-based peridynamics, we can directly relate peridynamic forces and classical stress tensors. Now, we are expressing our peridynamic force in terms of first Piola-Kirchhoff stress tensor, which is shown as P, and shape tensor, which is shown as K in the slide. And our shape tensor can be expressed in terms of influence function as shown in the last equation in the slide. Although non-ordinary state-based peridynamics is very suitable to link classical continuum mechanics and peridynamics, it has zero energy mode problem. Even under steady-state conditions, we can observe unphysical oscillations in the displacement field. To overcome this problem, Dr. Seeling introduced a stabilization term which is introduced in peridynamic force expression as shown in the peridynamic force definition in the slide. Here, C is the difference between the deformation state and average deformation gradient calculated from peridynamics, and W0 is related to influence function. G is a constant parameter. In peridynamic simulations, we usually use circular horizon shape for 2D domains and spherical horizon shapes for 3D domains. In this study, we investigated if we can choose other horizon shapes. In this study, we considered 2D domain and we investigated circular, irregular, and square shape horizons. To compare the difference between these three different horizon shapes, we considered two benchmark problems. The first one is the vibration of a square plate. As you can see here, the left side is fully fixed and we apply an initial uniaxial strain of 0.001. And the material properties are provided in the slide. To compare the results of these three different shapes, we choose a point which is far from the boundaries and central axis as shown as A in the slide. First, we modeled this problem by using ordinary state-based peridynamics. We also solved the same problem with finite element software ANSYS to compare our peridynamic results. Here you can see the variation of horizontal displacement of point A with time. As you see here, circular and irregular shapes agree very well with ANSYS results. However, there is a slight difference between the square horizon and ANSYS results. These plots show the variation of vertical displacement of point A with time. Again, circular and irregular shapes results match very well with ANSYS results. However, there is a significant difference between the square horizon and ANSYS results. We also solved the same problem by using non-ordinary state-based peridynamics. In this case, all horizon shapes agree very well with ANSYS results for the horizontal displacement. We also see a similar agreement for the vertical displacement. This shows that non-ordinary state-based peridynamics is not sensitive to horizon shape, which is not the case for the ordinary state-based peridynamics. Next, we considered a static problem which is plate under tension. In this case, we applied a tension load at the right edge while fixing the plate at the left edge. Again, we first solved this problem by using ordinary state-based peridynamics, and we observed slight difference for square horizon for horizontal displacement results with ANSYS. For vertical displacement, the difference is much more obvious. Although circular and irregular shapes agree very well with the ANSYS results, square horizon couldn't capture the expected behavior. Next, we solved the same problem by using non-ordinary state-based peridynamics. As in the vibration of a plate problem, all horizon shapes agree very well with ANSYS results for the horizontal displacement. We also see a similar agreement for the vertical displacement. Again, we can conclude that for static problems, non-ordinary state-based peridynamics is not sensitive to horizon shapes. As a final remark, in this study, we investigated the effect of horizon shapes in peridynamics. We considered circular, irregular, and square horizon shapes. Our findings show that non-ordinary state-based peridynamics is not sensitive to horizon shapes, and square shape doesn't provide good results for ordinary state-based peridynamics. Finally, I would like to acknowledge Air Force Office of Scientific Research for their financial support for this study. Thank you very much for your attention.